Hello, welcome everybody to this session where we will cover service meshes and specifically Istio. We will begin with a brief explanation at the beginning, but later on there will be a hands-on demonstration of everything that we explain. I am Rinor Maloku, a field engineer at Solo, where I consult and collaborate with clients in the EMEA region. I co-authored the book Istio in Action together with Christian Posta, and you can reach out to me in any of the listed handles. With me is Kamesh.
Hello, everyone. Myself, Kamesh. I'm a field engineer at Solo, based out of Bangalore, India. I'm a long-time open source contributor to many projects like Tekton, Knative, Minikube, and all. I'm author of Knative Cookbook that I did a year ago, and happy to share the session with Rinor today. Back to you, Rinor.
Thanks. So Istio provides exciting capabilities to your apps, and it is for this reason that most presentations spend all of the time in the technical details, which is good, but in the process, we lose focus on what really matters. And it is the people that benefit from the service mesh that matter. This presentation brings the people at the foreground and shows what each role or persona within a team can gain out of the service mesh. But to answer this, we need to initially know how we got to service meshes. Kamesh, can you help us understand that?
Oh, yeah. So let's go a bit behind, right? Way back to the beginning. And start with a Big Bang theory. This is not the Big Bang that we usually know about. This is a Big Bang that we went from monolithic to microservices. So how do we start breaking the applications into smaller pieces? So what gave with that is that we got a lot of benefits when we actually moved from monolithic to microservice. There were strong module boundaries, which means that applications could be built independently and deployed independently. There is also technology diversity, which means that I can build really polyglot applications and then deploy them into cloud or wherever my data center is. But the world of microservice is not all about sunshine and rainbows. Teams will quickly discover there are issues and get confused with, such as where is my service failing, which node in the cloud my service failing, and even my system is secure, etc., etc. Rinor, can you explain how teams can handle this?
Oh, yeah. So initially, the team should be aware that there are trade-offs when adopting microservices, because every strength has a weakness, and it is no difference here. Henry James made this lovely observation that applies about individuals, but it works just as well to systems. The observation is that every strength that an individual has, in our case a system has, necessarily brings with it weaknesses of which it is an inherent part of. In the case of microservices, those inherent weaknesses are operational complexity and the distributed computing nature of microservices. Having many smaller services requires automation for the operations of all of those, which becomes rather complex. The distributed nature of microservices brings with it a host of other issues, such as the network not being reliable and having observability over all the services is really difficult. Finally, all of the service-to-service communication needs to be secure, and that is as well a challenge. The good news is that all of those have solutions. Let's see those. So initially, operational complexity is more or less a solved problem. Docker makes it really simple to package the application and its dependencies into a shippable container. Then Kubernetes can run this container in any of the nodes that are part of the cluster it manages. As a service operator, you don't have to think about what nodes the services are running, if those are healthy, if the services are healthy. Kubernetes does it all for you. Meanwhile, the other issues that crop up because of the distributed nature of microservices, such as network not being reliable and then having latency and so on, all of those can be resolved with additional code. And understandably, you need to configure it as well. When a failure bubbles up to the client, as indicated by the red arrow, it is rather difficult to localize which service caused the failure. Is it A, B, or C? We solve this by instrumenting applications to generate metrics and traces, which means that you need to add additional code and configuration to your services. Security is a rather difficult problem to solve. Static IPs, which previously could be used as a means to authenticate a client, are not a source of truth anymore. considering the ephemeral nature of workloads running in Kubernetes. Many enterprises feel secure by simply allowing clear text traffic between services and only securing ingress and egress traffic. But that couldn't be farther from the truth. It is a false sense of security because traffic leaving one workload and going to another will go across nodes, and in between there will be many networking devices, and all of those represent a liability where the traffic can be read and seen, making your user information not safe. So as we see, what happens gradually is that by solving all of these weaknesses of microservice architectures, our services become bloated with code that is entirely not related to our business. This makes our team less productive. Instead of focusing on adding business differentiating features, they have to develop, maintain, and configure all of those libraries just to contain the issues that crop up when we adopt microservices. Thus, deadlines are missed, and the project manager is sad as well. And we quickly go from the happy team to a sad team. So you all be thinking that there must be an effective solution to this problem. And that is a service mesh. The service mesh pattern suggests that instead of adding all the code to the services, what we can do is we can have a sidecar and then just redirect all of the traffic to the sidecar and let the sidecar handle that. So it is the sidecar's responsibility to handle authentication of end users, encryption of traffic, service discovery, resiliency, generation of metrics, and making all of those available, all the metrics available to the metric servers and traces servers. Understandably, the sidecar must be configurable to meet the needs of all services. And for that, we have the following split. We have the split between the data plane and the control plane. The data plane is comprised of all the services and the sidecars, and the control plane is what reads the Kubernetes API and learns about the services running in the cluster, then generates configuration and pushes this to the sidecar proxies. And this way, we manage how a service to service communicates. Additionally, and what is even more important, our engineers can customize the configuration by using YAML resources and applying those to the API server. The event of the resource that gets applied is picked up by Istio and it is pushed to the sidecars. To take a concrete example, the security engineer can define a policy that configures service B to accept traffic only from service A and requests from any other service are rejected. Kamesh, I think I got the people excited. Can we just see those capabilities in action?
Yeah, totally, Rinor. Let's go to the demo.
Detailed instructions on how to install Istio onto your platform is available as part of the Istio Get Started guide. At the very minimum, we need what is called as an Istio CTL, a command line tool to interact with Istio resources. I already have the tool downloaded onto my system, and let me go check the version of what I have. I have 1.12.2 on my system. And as the version command reports, I don't have any Istio pods running on my Kubernetes cluster. That's exactly what we are going to do next. To install Istio, we need to run istioctl install command. I'm just going to copy paste the command from my clipboard, and it says Istio install a profile called as demo. There are multiple profiles available. You can use them based on your context. And I'm going to set one value called as global proxy privilege equal to true. Let's not worry about this value for now. I'll come back to that at a later point of the demo. And then once I have this, so this is going to install. It's going to take a few seconds for us to get Istio installed onto our system. And there we go. Our Istio is installed on our cluster and we are good to get our services onto the mesh. So let's go and check. Let's start a watch of my thing. I'm going to go kgpo on my cluster. Let me see this. So right now my services doesn't have a sidecar. So one of the things what you're going to do next is to bring our services into the Istio service mesh. I have to basically label the namespace with a label called as Istio injection enabled equal to true. Let's go ahead and do that. kubectl label namespace Istio in action Istio injection equal to enabled. So So now I label the namespace. This is a very basic thing that is required to get your services into the service mesh. Now what basically this command will do is, like any namespace that have this label, Istio will by default go ahead and inject the Istio sidecar proxy into all the service pods that is running on that particular namespace. So let's go ahead and do the restart of the apps so that it picks up these things. And as you see right now, the services which we are running with one of one are right now going to the state of 0/2, which means there is one pod, which is the Istio proxy pod, that gets injected into all these service pods. In few seconds, you see that our service pods has got the Istio proxy injected into them. The next step for us is to configure the gateway to allow the traffic into our service mesh. Perfect. We now have all our services into the service mesh, but we are yet to configure a route to reach to these services. If you remember earlier, we used kubectl port forward to get to our service A. But to leverage the power of service mesh, we need to create two Istio custom resources, one a gateway that configures that's an Istio custom resource workload that admits the traffic into the Kubernetes cluster via the service mesh, and a route, also we call as a virtual service, that decides what to do once the traffic is admitted by the gateway and where should I route it. So as part of the Istio installation we did earlier, there was a service which got created which is called as an ingress gateway. So let's go and check the service. Just going to copy, paste the command here. And we got an Istio ingress gateway service that has an IP address and listening here. In fact, we should also have a corresponding pod called as an Istio ingress gateway pod that handles this particular custom resource related things that has to be done once the traffic is admitted, right? So to use this particular custom resource, what you have to do is, like, we have to go create a gateway resource, which is another Istio custom resource as discussed earlier, and the custom resource has to go through the Istio ingress gateway. Okay, if you remember that, we use the same label here and we're using the same label here as well. And we said listen on port 80 and allow all host. In fact, we can also define specific host to allow, but in this case, I'm giving all host for the simplicity of the demo. As we discussed earlier, I should also have a virtual service that should basically leverage this gateway, this particular service A gateway, and route the traffic. Once the traffic is admitted into this gateway, this virtual service decides where to route the traffic to. In this case, I'm going to route the traffic to my destination, which is called a service A, which is nothing but the service which we already deployed and were using earlier. All right, let's go ahead and create these resources to start routing the traffic into the cluster. There we go. We got the resource available for us to do this. In order to use this gateway, we have to use the Istio ingress gateway IP address to route the traffic to. So to do that, for the convenience sake, I'm just going to store that particular value in an environment variable called as Istio ingress gateway IP address. Right? Once I have this, I'm going to start sending traffic into the cluster. So for the later use, I'm just going to start sending the traffic multiple times. In fact, start sending, then you should see the response coming here. I'm just going to send a lot of requests continuously because we need to observe few things at the later part of the demo. So I'll just keep sending some load so that the load gets piled up into the Istio system. All right. So now we are good that we have got the traffic into the cluster. But if you remember, we have not yet nailed down our problem. The problem of why the service failures are happening. Since the distributed computing is complex, so we need to have a set of tools that helps us to troubleshoot and fix the problems. In other words, we should have our system observable. Istio does provide us with a set of tools that will allow us to observe our service mesh. That is technically observing the services that were deployed as part of the service mesh. Out of the box, Istio generates access logs and metrics that could be used by tools like Grafana, ELK, and Datadog to generate and visualize the data. So let's go and inspect one such log from our proxy sidecar of service A to see if it gets a clue on what's going wrong with our failures. And there we go. We see a bunch of 500 errors that are coming out of this, right? If you observe this one such error that's going outbound here, it goes to service C. So which giving us a clue that there is some problem with the service C, right? It's going from service A to service C, and now we see there is a problem with service C, which is giving 500 back to me. But you also need some additional data or metrics that requires us to validate this particular clue that we got and see how many requests are failing and how many requests are succeeding. To do that, we can leverage on the Prometheus data metrics that Istio by default generates for you. Let's go and run a query to get our Prometheus data. Copy the command and paste it here. There we go. So I just run the command that gets me the number of requests that were successful. In this case, there were 500 requests which failed and there were 336 requests which were successful. But hold on. So this is okay if I do a small demo like what I'm showing to you people right now. But if you have a large cluster, you need some kind of a mechanism where which you can monitor and observe these data and raise alarms. Of course, Istio does provide you with a set of add-ons that could be integrated with it. So let's go ahead and install those add-ons and see what it can do for us. So there's a bunch of parts that needs to be run right now. So let's wait for the parts to be coming up on this namespace. And let's go and open the dashboard later. So I'm just going to open the Grafana dashboard. So let me go copy the command that's required there. So, but we have to wait for some time for the parts to be up. Okay, there we go. So we got all the parts up and running for us. So let's go and open the Grafana dashboard and we should be, let's go and open the Grafana dashboard and we should go to the workload dashboard and outbound services and we should see a lot of errors here, right? As you see on my screen, we should see a lot of success, non-5xx responses, so outgoing success rate, and then we should also see a bunch of service C's is failing, right? It's giving 500 for us. So this gives us kind of a real-time monitoring on our service mesh to see what is going right and what is going wrong. So, but we also have another tool called as Kiali. So that helps us to observe the entire service mesh from one shot. Okay, let's go and open that also, Istio CTL dashboard. And then I'm going to open Kiali. And there we go. Kiali is open for us. And then if I go to the namespace, let me go and find out the graph. And let me go and add few things here. So the default namespace is there. The Istio namespace is there. And let's do a few little things, right? I'm just going to add these things ready so that for the observation. Now, if you see this dashboard here, and then you see the service going here, service A, and then service C is failing here. And technically, it also gives you data that version 2 of the service is failure, whereas the version 1 is successful. That's precisely the reason why we get 50% success rate here, and the rest are all failing for us, right? And this makes our service operator happy because he was able to find out where exactly the problem is and how we can tell the respective teams to go and fix the problem. But our developer is still not happy because we have not found the way by which I can fix these issues without affecting the end user. Because right now the end user is getting the response failed, which is not good in many cases. Let's go and help our developer to fix that problem.
Since most of the time it is difficult to fix the service on the fly, but at least we should prevent the request from reaching the erroneous service. In this case, version 2 of service C. To do that, we leverage on Istio's traffic management capabilities to route all the traffic to version 1 of service C. In order to do that, we create a new Istio custom resource called as destination rule. As the name suggests, destination rule helps us to define the rules on how to select a destination. In this case, we are defining a destination rule for service C, and we say select them based on the labels version v1 and version v2, and give them appropriate names, which we'll be using as in the virtual service that we define for service C. And then we say the destination to be service C and use a subset version v1. Now, all the traffic gets routed to version v1 once we apply this. Let's go and apply this. I'm going to go copy, create the destination rule, and then I'm just going to go ahead and create the route as well, and then start sending some requests so that we'll go to our Kiali dashboards to see what's happening, right? Let's refresh this one. Let's see what's happening. It's loading the graph. It gets some time to get the traffic into it. While we do that, let's go and refresh our UI, and you should see no longer failing services coming up as part of the UI. Now the end user is happy because he no longer gets errors. So our developers as well, because we are not sending erroneous response to the end users.
And now let's go to Kiali and then refresh again. Now you should see the success rate bumped from 50% to 100% in this case, right? But still, we have one more problem to solve. Let me stop this one. Now we have got all the 100% of the traffic going to version 1 of service C, thereby preventing the end users accidentally getting routed to the erroneous service. But we still need the traffic to go to version 2 of the service C so that our developers can find out what's going wrong and build a fix for it. To do that, we leverage on another traffic management capability of Istio called as traffic mirroring. With traffic mirroring, we route all the traffic arriving at one destination to another destination defined by a percentage. In this case, we say whatever traffic that comes to service C version V1, also mirror it to version 2 of service C up 100%. By doing this, we'll be able to find out what's going wrong with our service C version 2 as well. Let's go and apply this one. And once we apply this, if we go back to our Kiali console, we should still see the traffic getting routed to both, and our success rate is almost 100. Now, our developers is also happy because he's successfully guarded the end user from getting an erroneous response, as well as he knows what's going wrong to work on a fix for it. Excellent. Now our developers are very happy because they were able to reproduce the issue and work on to fix it. But as part of our routine security audit that we ran on our data centers, we found few security issues. Let's understand what they are and see how Istio's capabilities could help us to fix them. In order to understand the first issue, I'm going to run a TCP dump on our service A. Let's see the dump going, and then I'm going to give a call from within a mesh. That is, I'm going to call service C from a service A. So let me go and do that. And we get a response, and we see that the service traffic is still goes encrypted. But in the real-time scenarios, your call to a service mesh could potentially come from outside your data center, like probably your replicated data center across geographies, or another computer or a node, or a third-party service that is giving a call, etc. So let's see a call from one of our legacy systems that is trying to call our service A. Let me try to run a call and see what happens. And now you see this traffic. I'm going to stop the TCP dump. And if you go and observe the traffic here, the traffic goes unencrypted. This is a potential security issue because any hacker, in fact, trying to sniff your traffic can read sensitive data. In order to fix this, we are going to leverage on another Istio custom resource called as peer authentication. With peer authentication, we are going to enable mutual TLS within the service mesh, which means any client who is trying to call a service within the mesh has to authenticate themselves in order to get the response. So let's try applying that. I'm going to apply peers authentication. There we go. It got applied. And now let me start the TCP dump again and see what happens. And then let it go. And then I'm going to do a legacy call again. And obviously, the call gets terminated with the error code 56, which means that it is not allowed because the legacy system has not authenticated themselves. And you also see the traffic doesn't come into a cluster at all. So in this way, what we can do is that we can let our clients and consumers know that you have to authenticate yourself to access a service within the service mesh. Cool. We now fixed one of the findings of our security audit. But we still have one more thing to fix. That is the open access policy. What is this open access policy is all about? So let me explain that with an example. Let's assume that I'm going to give a call from service B. When I do this call, as expected, I'm going to call service A from service B. And this is going to go through, obviously. And again, I'm going to give another call to service C V1 from service B. Or service C V1 calling service B, either way. And now this should also go through, right? But as per our architecture, I want only service A to be the path to service C and service B. And you can question what could be wrong with this approach. With open access policy, you're opening up a security thread
where someone can assume or impersonate the identity of the service to gain access. In order to fix this, we go with a principle called as least privilege. What I mean by that, as I said earlier, we're going to keep only service A to be the only route to service B or service C. In order to do that, we are going to leverage another Istio custom resource called as authorization policy. What I defined in this we are going to define 3 authorization policies. For the first one, where I say we define for service A, and we say that the service A could be accessible only by Istio Ingress Gateway service account that is residing in Istio system namespace. In short, I'm going to allow the access to service A only via Istio Ingress Gateway. And then I'm going to define one for service B, which says that the service B could only be accessed using via service A, the service account service A. And lastly, I'm also going to say that service C, again, is also accessible only by a service account called as service A. In this way, I'm kind of opening up the access to my services on need basis. Let's go and apply these things and see what happens. So I'm going to first apply the auth policy, the first auth policy. So things going to go through, everything works well. And then let's go and apply the other 2 as well. Let's go apply service A. Taking a bit of time to apply. Let's got created. And then I'm going to apply service B. That's also going to go through in a second. And finally, the one for the service C. And now the service C access policy also got applied. And now when we go back, all good. Now when I go back and give the same old calls, that is calling a service A from service B, technically I should get an RBAC denied error. So let me go and do that right now. Let me go and call this. When I do this, technically I should get an error. There we go. We see an HTTP 403 forbidden because service B is not allowed to call service A. Similarly, I'm just going to give another call, the same old call which we gave earlier. So let me go and give this again. I'm going to copy this and paste the command again. Let's go and give the call again. And hopefully this should also give you the same old error. Let's wait and see. And there we go. We got the similar error for this as forbidden because service C is not allowed to call service B. But when you go back to the browser, things should work as expected as earlier, right? Because there's nothing changed to the outside world, because the outside world, the service A is the only route to service B and service C, and service A is being called via an ingress gateway. Perfect. As you see, the rich feature set of Istio helps us to identify and fix the problems quickly. We just skim the surface of Istio's features. Please do check our resources slides for more valuable links to get started with your Istio journey. Back to you, Rinor.
Thanks, Kamesh, for the demo. Hopefully you found this session insightful and it had the goal to excite you for more. We recommend any of the following resources to do further learning. Thanks.